So far in our analysis of IMC-based PID controller tuning parameter design, it's been pretty nice. We've been able to look at a first order and second order internal model and derive the tuning parameters all as a nice function of lambda. But once we dive a little bit deeper into the real world and start taking into account things such as dead time, it does get a bit more tricky. And so what I'll do in this video is go over how we can use the IMC method to control a process model that has intrinsic lag in it. And so we're going to have to start worrying about this thing called dead time, which is mathematically represented by this exponential term here. And so before I get down into going through how we will build our internal model control, we're going to first look at how we the equation governing our standard feedback controller GC. And GC, as we've defined previously, was equivalent to Q, the internal model control, divided by 1 minus G tilde times Q. And Q, by definition, was equivalent to Q tilde times F, where Q tilde, I should write this here, Q tilde was equivalent to the inverse of the stable portion of our given process model, our internal model. And G tilde we could decompose into its stable portion, which was G tilde minus, and its unstable portion G tilde plus. And so in this case, because we now have this dead time component, that's where we're going to toss in into our G tilde plus area. And so if we continue to rewrite what our controller transfer function is and we expand it, we'll plug in the definition of Q and recognize that now GC is equal to Q tilde times our filter F divided by 1 minus G tilde times F. We now plug in what we know G tilde was equal to, which was, this should actually say G tilde times Q. And so continuing, we see that we have C is equal to Q tilde times F divided by 1 minus, and then we have G minus tilde times G plus tilde, and then times Q, and Q was equivalent to Q tilde F, and sorry, this is getting a little messy, but Q tilde F was equal to G minus tilde inverse times F. And what we'll see here is that we can now cancel out the in the denominator of our standard controller feedback function these G tilde minus terms. And so our equation will now look like G tilde minus, G tilde minus inverse times our filter divided by 1 minus the unstable portion of our feedback controller times the filter. And this is a key point to get to when we're dealing with lag in our system. And so now that we've done that, we can move on and begin more closely analyzing the given model that we're working with. And so what we're going to say is G tilde minus, as we've defined up here, was equal to Kp times the exponent of minus theta s over tau p s plus 1. We're going to decompose g tilde into two separate functions, and we're going to multiply them together. We're going to use a first order PID approximation in order to approximate this exponential term here, which represents the time delay or the dead time in our system. And we're going to let this now be equal to Kp over tau ps plus 1 times, and what the PID approximation tells us is that exponent minus theta s is equal to theta over 2s plus 1 over plus theta over 2s plus 1. And what we'll note here is this is the stable portion of g tilde. So this is g tilde minus, and g tilde minus is all of this part here, because this is a negative pole, which is this term here, the plus theta over 2s plus 1, because theta is time, which must be positive, so this must be a positive pole. We know tau p, a process gain time constant, must also be a positive value as well. So this is all g tilde minus, and then this term up top is g tilde plus, our unstable part. And so now that we've identified these portions, we can plug them into our equation that we have for our standard feedback controller. And so now if we also will take into account that f is equivalent to 1 over lambda s plus 1, which is our generic filter with our tuning parameter of interest in our IMC model, what we get when we rewrite our standardized controller feedback function, transfer function for a first order process with dead time is this. So we'd have 1 over Kp times the quantity of our process time constant tau s plus 1 times theta over 2 times s plus 1 quantity divided by lambda plus theta over 2 times this quantity times s. And if we now expand the numerator and do some algebraic rearrangements, we will find that this is equal to 1 over Kp times theta over 2 times tau ps squared plus quantity tau p plus theta over 2 times s plus 1 divided by lambda plus theta over 2 quantity times s. We can now rewrite this GC, in the form of what a standardized PID controller is, to recognize that the controller gain constant we should go with based on this IMC method is equivalent to tau p plus theta over 2 divided by your process gain constant Kp times quantity lambda plus theta over 2. Our integral time constant in our PID controller should be equivalent to tau p plus theta over 2. And finally, our derivative time constant tau d should be equivalent to tau p times theta divided by 2 tau p plus theta. And so this is what we find we should implement for our PID tuning parameters based on the IMC method for a first order process with lag or dead time. And so the dead time is taken into account by these theta parameters, and we'll note how these every single one of our PID controller tuning parameters are functions of our theta, but also we've got this lambda term that is affecting what gain we should go with, and this lambda is what allows us to adjust the trade-off between robustness and performance. And so this summarizes how we can get these tuning parameters. An important note here is that this is an ideal PID controller, because what we'll note here in this GC function is that the degree of the numerator exceeded that of the denominator, and consequently this system is what's referred to as aphysical. It doesn't really exist, and so in practice we would modify our filter, which was this this term here. We would make this a second order filter by squaring this, but it would yield a result that is not a PID controller. And so for the sake of determining what PID tuning parameters we should go with based on the IMC method, this is what we had to do. And so the approximation also that we made at this point when we went with a first order PID approximation is something that in the textbooks they're only doing for first order processes. And so if we're working with integrator processes or game processes, instead of PID approximations, they'll turn to Taylor series approximations, just a first order Taylor series approximation, and it's all so that we end up finding what our PID tuning parameters should be. And final note is that these functions are things that we look up in tables. So if we are given some kind of process model and we see, so in practice what an engineer would do is you would be given this process model, you would recognize that it's a first order process by looking at the degree of the denominator. You would see that it's a first order process. You would see that we've got a dead time present. We would go to a table, and people have already worked out that these are the appropriate tuning parameters to go with. And so this was kind of an overview on the derivation behind it, because it is common in process control classes that you would be expected to be able to derive these kinds of things. And so I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.